Hello and welcome to lecture 4 of this unit of Phys 1101, and in this lecture we meet the third and last of Newton's laws of motion. We've actually already seen the main idea of this whole lecture. We saw way back in the last unit that when my hand pushes on the wall pushes back on my hand. All forces result from interactions between two objects, and each of the objects exerts a force on the other. So whenever one object pushes or pulls on another, the second object pushes or pulls back. These pairs of forces are called interaction pairs. So the force that my hand exerts on the wall and the force that the wall exerts on my hand are the two forces resulting from the interaction between my hand and the wall, and we say that these two forces form an interaction pair. Now we come to Newton's third law, which is a statement about interaction pairs, and you've probably learned it in a previous physics course, and you probably learned it by this original statement that Newton made. But I actually think we do a great disservice to ourselves and to Newton by learning it this way, because the meaning is unclear. The reason the meaning is unclear is that Newton wrote this down in the 1600s, and the English language has changed a fair bit since then. What scientists meant by action at that time is what we now call a force. So to start with, we could rewrite it: for every force, there's an equal and opposite reaction force. That's still not as clear as we could make it, though, because it would be nice to have this fact that the agent and target get reversed in the two forces in an interaction pair encapsulated in the law. Also, it begs the question, which is the force and which is the reaction force, which is an artificial question. Each of the forces in the pair is the reaction to the other one. So here's a more modern statement. If object A exerts a force on object B, then B exerts a force back on A, which is equal in magnitude and opposite in direction. Well, that doesn't roll off the tongue quite as nicely as Newton's original statement. If you want a nice, brief, pithy statement, you go to the mathematical one like this. And now it's clear the force that A exerts on B is of the same magnitude that the force that B exerts on A, and this negative sign is saying that the force vectors point in opposite directions. Here's a common mistake that I often see students make. Think about a box on a table on a floor, right? We'll call them B, T, and F for short. And students will often misidentify the normal and the weight as an interaction pair. The reason they make that mistake is that it seems plausible. These two forces are in opposite directions, and if you understand Newton's second law, then you realize they also have the same magnitude. But of course, that's actually only true in a simple case like this. All you have to do is put the box on a slope, and all of a sudden the normal isn't in the opposite direction to the weight. But the real problem here is that the agents and targets are wrong. Remember that in an interaction pair, the agent and the target are just reversed between the two forces, but that's not going on here. These are both forces acting on the box, and they're by different agents. An interaction pair will always act on different objects because the target of one is the agent of the other. And so if we want to find the partner, the other force in the interaction pair with this normal, we have to look at the free body diagram of the table. And now you see that the normal that the table exerts on the box is the interaction partner with the normal that the box exerts on the table. Well, what about these weights? That leads us to something sort of a little surprising. These are exerted by the Earth. And so we have to go and look at the free body diagram of the Earth to find their partners. So here's the free body diagram of the Earth, ignoring the fact that the sun and the moon are exerting forces on it, and we're just focusing on the Earth's interaction with the box and the table. Because the Earth pulls down on the box and the table gravitationally, the box and the table must pull up on the Earth. And that seems surprising and perhaps even implausible, but we actually see evidence of this sort of thing all the time, especially in a place like Cape Breton here. Just think of the tides. the Earth is pulling on the moon, and that's what keeps the moon in its orbit. And in turn, the moon pulls back on the Earth, and that's part of what causes the tides. One more thing about this, if you look carefully, you'll notice here, this normal force, its partner in the interaction pair is also a normal force. And each of these weights is partnered with another weight. And in fact, you'll see that this is always the case. Now, I've actually never seen this stated in a textbook. And although I'm sure I'm not the first person to ever realize this, I'm going to claim this as my law since I've never seen anybody write it down. Maybe it's one of these things that's just so obvious to practicing physicists that they never think to state it. So I'm going to call it Jeff's law of interaction pairs. The two forces in an interaction pair are always of the same type. Well, here's one of these ridiculous questions that only children and scientists, who after all are just children who never grew up, will ever ask. How do you walk? Well, let's start off by thinking about this person walking, and let's say they're speeding up to the left. And so here's a free body diagram. And if they're speeding up to the left, then F net must point left. And we now ask, well, what is the force responsible for that? You may say that you speed up because you exert a force on yourself, but remember, you can't pick yourself up by your shoelaces, and by the same token, you cannot push yourself to make yourself speed up. The only thing you're in contact with is the ground. And so it must be the friction force, if your foot isn't slipping, then a static friction between the ground and you. And that is because you are trying to move your foot back on the ground, so you exert a friction force back on the ground, and it is an interaction pair with a force that is then exerted on you. And this is an example of what's called a propulsive force, where an object exerts a force back on its surroundings so that its surroundings exert a forward force on it. Many propulsive forces are frictions, but not all. Here's a very practical problem. Let's look at a car towing a trailer. And we're told that the car's wheels push backward on the road with a force of 2,000 newtons, and that causes the car and the trailer to speed up. And we want to know what the force is that the trailer hitch exerts on the trailer. So, I mean, this is when you're designing things like trailer hitches, you need to be able to design them strong enough to exert the sorts of forces that you expect. And so this sort of a calculation comes up. But let's start with this statement that the car's wheels push backward on the road. Well, when you push down on the accelerator on your car, you're making the wheels spin faster. That makes them push back on the road. And so this results in another propulsive force. And so the road pushes forward on the car. Now, if the wheels don't skid, that's a static friction. That might confuse you because the car is moving. But remember, what determines whether it's static or kinetic is whether there's slipping. And as long as the tires don't skid, then there's no slipping, and that's a static friction. Then the car pulls forward via the hitch on the trailer, and the trailer pulls back on the car. And so I'll call those F car on trailer and F trailer on car. And that makes it pretty clear that that's an interaction pair. And so those will have equal magnitude. And similarly, this static friction force forward on the car, that's 2,000 newtons. And what we want is F car on trailer. That's what we're looking for. So I've already written out the y components. They're pretty uninteresting. They're just telling us that the weights and the normals have the same magnitudes. And so now let's do this part. So F car on trailer equals. Now here's a detail of Newton's second law that isn't often explicitly stated. The sum of forces on an object equals the mass of that object times its acceleration. And so this is the mass of the trailer that goes here. And similarly, here we've got Fs minus the force that the trailer exerts on the car, and that has to equal the mass of the car, Ax. And if the car and the trailer move together, those accelerations have to be the same. So I've used the same symbol for them. And now let's go about solving for what we're looking for, which is this force right here. So these aren't going to help us. They're all in different variables that don't appear, but let's count our unknowns. We don't know this. We don't know this. We don't know the acceleration, but we do know both masses. They're given above, 800 and 200 kilograms. And we know this static friction. It's that 2,000 newtons. Well, that means we've got 3 unknowns and only 2 equations, but we've got another equation. F car on trailer, Newton's third law tells us, is the negative F trailer on car. And just to simplify notation, let's call that capital F. And so, now rewriting these, we have that F equals M trailer AX and Fs minus F is MCAX. And now we can solve this, and the strategy is going to be to solve for AX and then substitute that in here. So I'm going to pause the video and do that, and you do it too. So I've finished solving, and you should check your solution and see that you came up with this, and if the algebra confuses you, well, have a look over it. So this is what we get. We get that the force that the car is exerting on the trailer is just the static friction over this. And if you look at how the units work out, kilograms take out kilograms down here, and that's basically 4. So we get 2,000 newtons over 4 plus 1 is 5. And so that is 400 newtons. Good, we've got newtons as we must because this is a force. A lot of people have a serious misunderstanding of rocket propulsion. I've often heard people say that the rocket, when it's shooting the gases out the back, the fire, is pushing against the ground. But that's not true at all. Think about what that would do. If that were the case, then as the rocket moved, once it was away from the ground, it would no longer accelerate. But the whole point of rocket propulsion is that you can use it out in space when there's no ground nearby. So what's really going on? Well, this is a propulsive force, and it's a propulsive force which relies relentlessly on Newton's third law. The rocket, as it burns its fuel, is shooting the gases at high speed out the back. That means it's pushing on the gases. Well, Newton's third law tells us that the gases push back on the rocket. And so the rocket has a large force which accelerates it forward.